Hey there and welcome. I am so glad you're here. In this video we are diving into the fascinating world of heat transfer and how it forms the bedrock of building simulation. If you ever wonder how we predict a building's energy use or figure out why a room gets too cold or too hot, you're in the right place. We'll be connecting the three main ways heat moves: conduction, convection, and radiation, to real-world stuff you actually see in buildings simulations. So, what are we going to talk about? So we'll start with how heat moves through solid materials like walls and floors. That's conduction. Then we'll talk about how air and other fluids move our heat around, which is convection. After that, we explore how you can feel heat without even touching something. That's to radiation. Once we have the handle on these three, we'll see how they become the inputs and outputs in building simulation software. And finally, we'll learn a crucial skill: knowing when to use a simple steady model versus a more detailed transient one. By the end of this video, you will be a pro at spotting the three heat transfer modes in real building parts like walls, pipes, coils, and roofs. You'll also know what are the inputs and outputs of a building model. And finally, you will know when a simple steady state approach is good enough and when you really need a more complex transient model, especially for things like those sun-exposed walls that change throughout the day. The ultimate goal is for you to be able to confidently choose the right analysis for the job and explain why you made the choice. Sounds good? Let's get started with a quick warm-up. Before we get into any jargon, let's use our intuition. Check out these three scenarios and think about which heat transfer mechanism is at play. A metal door feels cold on a winter day when you touch it. This is a classic example of conduction. When you touch the cold material, the cold metal door, heat flows from your warm hand to the colder door through direct contact. In the middle part, we see warm air from a supply vent that hits your hand. This is convection. The warm air is physically moving and carrying heat with it, transferring that energy to your hand. And finally, in C, you feel warmth from a sunlight window even without touching it. And this is the one is radiation. The sun's energy is traveling as waves through space and the glass, and you feel the warmth when the waves hit your skin. You don't need a solid object or moving air for this to happen. Now that we have a feel of this concept, let's look at each of them more in detail. First up, conduction. Imagine a heat moving through a solid object, like a wall, from a hot side to a cold side. This is driven by a temperature gradient, meaning heat always wants to go from where it's hot to where it's not. Then, in building design, we often talk about R values or thermal resistance. Think of R value as a material resistance to heat flow. The higher the R value, the better the insulator. We use this concept to figure out how much heat is conducted through things like walls and roofs. A key thing to remember is that the heat flow through solids is governed by the Fourier's law that is there from the beginning of the slide. This law links the amount of heat to the material's thermal conductivity and the temperature difference. We can even combine R values for different layers of a wall, like insulation and drywall, to find the total resistance. One more thing. When you can use a simple steady-state model depends on the object. For a thin window pane, heat flow is pretty much constant, but for a thick concrete wall, which has a lot of thermal mass, it takes a long time for heat to move through it. So for those big, heavy walls, you'll need a transient model that can account for how heat builds up and release over the time. So now let's move on to the second topic, that is convection. Convection is all about heat transfer to a moving fluid like air or water. So the basic principle is captured by Newton's law of cooling that is there. This law says that the heat flow is proportional to the temperature difference between a surface and the surrounding fluid. So the constant of proportionality is called the convective heat transfer coefficient, or the HC. So I'm gonna do this definition again. Yeah, let's do it again with the pointer. This law says that the heat flow is proportional to the temperature difference that is here between the surface and the fluids, and the constant is this constant of proportionality is the heat transfer coefficient here, and this is the area of the surface. So there are two main types of convection: forced and natural convection. Forced convection is when a fan or pump is actively pushing the fluid. Think about the air blowing out of an air conditioning vent in a duct or a pump pushing water through a boiler. Natural convection or free convection happens on its own due to buoyancy. A great example is the warm air rising of a radiator, or how air circulation around the inside of a window on a cold day. Then we have the choice of to choose HC. An HC value in a simulation. This choice depends on whether you have forced or natural convection, because the two act very differently. Now let's talk about radiation. This is the transfer of heat through electromagnetic waves, and it doesn't need a medium like air or a solid object to happen. Think about feeling the sun's warmth on your skin or the heat from a campfire. Building surfaces are constantly exchanging radiation with each other and with the environment. The amount of radiation depends on the surface temperatures, raised to the fourth power that you can see here, the sign. And the emissivity, that is this epsilon here. Emissivity is a measure of how well a surface can radiate, or it's also related somehow to absorb energy. Then we have in building simulations, we use something called view factors to figure out how much one surface sees another. Imagine you're standing in a room. You can see a certain portion of the walls, ceilings, and floor. The view factor is a number that describes that relationship. To make things simpler, we often use a clever trick that called linearization. We can define an effective radiation coefficient, HR, that combines the radiation effects with convection. This lets us lump them together into one easy-to-use number for our calculations. It's a great example of how we simplify complex physics for practical use in building a simulation. So how do all these concepts get used in a simulation program? Well, first we have the inputs. You'll input data that describes these heat transfer models. For conduction, you'll enter things like R values or thermal conductivity. For convection, you'll provide the HC value. And for radiation, you'll need the surface emissivities and view factors. You'll also set up the surrounding conditions like the air temperature outside or the temperature of the sky. The outputs. So the simulation software then crunches all the numbers to give you some key outputs. This includes things like the surface temperatures, the rate of heat flux through a wall, and ultimately the heating and cooling loads for the building. These loads are what determine how big your HVAC system needs to be. And one of the most important steps is always documenting your assumptions. This way, if someone else looks at your work, they know exactly what you did and why. Then we have this critical decision in building simulation. Steady state assumes that everything is constant over time. It's great for quick, high-level analysis or for components with low thermal capacitance with a thin window. It's a simple, fast approach. However, for a building with a lot of thermal mass, like a concrete building, or one that experiences major temperature swings throughout the day, you need a transient model. This type of model accounts for how heat is stored in the building envelope during the day and released at night, a phenomenon known as lag and attenuation. As a quick rule of thumb, always compare the time it takes for a temperature change to happen outside to how long it takes for a building's material to respond. This will help you to decide which approach is the best. So finally, we have some key takeaways. So that three modes map directly to simulation parameters and loads. Then we should remember that the heat transfer parameters are important inputs for our simulations. And finally, we know how to choose between steady state and versus transient simulations based on mass. So to finalize, I invite you to continue learning. The world of building simulation is vast and there is always more to learn. If you want to dig deeper, here are a few topics to explore. Thermal bridges, those are in composite walls. This is a really important concept that explains how things like framing can create pathways for heat to escape, reducing a wall's overall R value and impacting energy loads. View factor methods for complete enclosures. If you are dealing with interior spaces that aren't simple parallel planes, these methods help you to accurately model how surfaces radiate heat to one another, which is essential for irregular geometries. Response factors or radiant time series (RTS) approaches. These are powerful techniques that let you capture that complex behavior of transient envelope dynamics without needing to run a full detailed transient model. They are a great way to get detailed answers efficiently. Thank you for watching. I hope this video helps you on your journey and to learn more about building simulations. We see you in the next video. Bye.